Let's jump right in. Artificial intelligence has achieved some truly remarkable progress recently. We all know it processes massive amounts of data, learns complex patterns, and assists us with everything from writing code to scientific research. It's genuinely incredible. But, beneath all those impressive capabilities lies a fundamental boundary, and it's a boundary we are just now beginning to cross.
So this brings us to the core limitation of modern AI. It learns brilliantly, sure, but only inside a fixed box that was entirely designed by humans. We design the architecture, we define the objectives, we establish the evaluation process. The system just gets better at solving problems inside that specific pre-built framework. But a really profound question remains. Can an AI system actually improve the framework itself? Can it examine its own performance, spot its limitations, and fundamentally adjust its own internal organization?
To answer that, here is the roadmap for our explainer today. We'll start with the fixed machine, then move to redesigning the frame, the energetic paradigm, controlling instability, structural balance and decoupling, and finally, wrap up with the future of intelligence.
All right, part 1, the fixed machine.
For most of AI's history, the division of labor was crystal clear, right? Humans built the architecture, and the machine executed it. Even today, when a system optimizes billions of parameters, it's still trapped inside a learning structure it didn't create. To really wrap our heads around this, we need to contrast two concepts. What we've had until now is object-level optimization. That is basically like tuning a car's engine to get better gas mileage. You're just improving performance within a fixed procedure. But the new frontier, that's meta-level optimization. This isn't just tuning the engine, it's the machine realizing it might need to invent a hover drive instead. It is improving the actual procedure that produces the performance. The machine gains access to its own underlying method. Moving on to part 2, redesigning the frame. Algorithm design is notoriously difficult. As humans, we tend to build designs that feel familiar or just mathematically elegant to us. But what if we took those human cognitive limits out of the equation entirely? Imagine a closed recursive cycle of algorithm discovery. The system generates new candidate structures, evaluates the performance signals, selects the variants that reduce error, retains the useful stuff, and then recombines them to create new trajectories. It is remarkably similar to biological evolution. The system can test and keep successful structures that we humans might completely ignore, just because they look messy or unintuitive to us. Which brings us to part 3, the energetic paradigm.
Now, you might be thinking, unrestricted self-modification sounds incredibly risky. And you'd be right. A useful system has to preserve stability. So how do we prevent this from just devolving into total structural chaos? Well, enter the energetic paradigm. You can think of it like navigating a physical landscape. In this context, energy means the organizational capacity required to sustain and change a state. It highlights a really profound truth. Intelligence isn't just the ability to calculate, it's the ability to manage transitions. Complex systems exist in environments with limited resources and strict constraints. They have to find pathways that actually work without exhausting those resources.
So, when evaluating a newly evolved algorithm, the system isn't merely chasing a high score. It's constantly balancing multiple components. We're talking computational cost, uncertainty, instability across iterations, fragility under change, and of course, achieved performance. It's kind of like building a house. You don't just want it built fast, you need it to survive a hurricane. The system is actively searching for a lower energy, stable configuration, a procedure that gets the job done with way less waste and lower vulnerability. Let's look at part 4, controlling instability. So how do we take these big theoretical concepts and practically apply them so the AI doesn't just spin out of control? Well, one major breakthrough is volatility adaptive memory. Traditional AI uses pretty fixed rules to discount older data, but a self-evolving system actually tracks its own volatility. When the learning process is super unstable and noisy, it aggressively forgets obsolete information so it doesn't get confused. Then, as it stabilizes, it starts retaining more history. So intelligent memory is truly conditional memory. It depends entirely on the current structural stability of the system itself. This system also does something I find incredibly clever. It treats positive and negative evidence asymmetrically. Positive signals, those are amplified to quickly expand, promising new paths, but negative signals are strictly capped. Why? Well, because if you accumulate too much negative evidence, you essentially build a permanent wall, and the system will never reconsider that path again. By capping it, the system preserves future reversibility. It avoids locking itself into a corner and keeps its options open.
This perfectly illustrates the concept of delayed strategy averaging. Learning happens in distinct phases. In phase 1, the early iterations, you have exploratory turbulence. It's exactly like when you're first clumsily learning to ride a bike. If the system memorizes this early wobbling noise, it absolutely contaminates its long-term average. So it deliberately ignores that early turbulent data, waits for phase 2, which is stabilization, and finally moves to phase 3, consolidation. It literally only commits to memory once a stable, reliable structure has actually emerged.
All right, part 5, structural balance and decoupling. A self-evolving system has to juggle a lot of competing needs. It needs to explore the unknown, absolutely, but it also has to exploit the things it already knows actually work. It manages this through something called dynamic annealing, which is basically a temporal reallocation of energy. Early on, it invests heavily in exploratory allocation. It tolerates noise and weird variations just to expand the possibilities. But eventually, all that variation becomes wasteful, so it dynamically shifts its resources towards stabilizing allocation. It starts focusing on precision, equilibrium, and really refining the best candidates it found. And here is perhaps the absolute most vital design choice in this entire process: decoupling. The subsystem that generates novel ideas simply cannot be the same subsystem that evaluates them. Think about it. Generation rewards novelty, evaluation rewards reliability. Combining them is like trying to be a wildly creative, free-flowing writer and a harsh, critical editor at the exact same time. You just end up with either timid ideas or really inaccurate judgment. Generation and judgment are totally distinct energetic functions, and they absolutely must be kept separated.
Finally, part 6, the future of intelligence.
So, where is this all heading? I mean, it's totally natural to feel a bit of anxiety about machines redesigning themselves, right? We wonder what our place is going to be in this new ecosystem. To answer that, let's consider the hierarchy of adaptation. AI has already pretty much mastered parameter and policy adaptation, and today, as we've discussed, we are seeing the dawn of algorithm adaptation. But look closely at those top 2 levels: objective adaptation and constraint adaptation. The system does not independently decide what problems matter or what constraints apply. Those elements remain strictly and entirely governed by humans. What this creates is a brand new, highly collaborative division of labor. We aren't becoming obsolete, we're essentially becoming landscape engineers. We formulate the complex problems, we define the strict constraints, and we interpret the scientific results. The machine, on the other hand, takes over structural exploration. It conducts these massive searches and generates candidates at speeds we could literally never match. Human judgment and machine exploration are performing perfect complementary functions. And this is exactly why we don't need to fear some unrestricted sci-fi style mutation. Valid recursive intelligence is actually highly controlled reorganization. For this to work, the system fundamentally requires a stable record of its previous states, reversible experimentation, independent verification, and a built-in, non-negotiable ability to reject revisions that might look good locally but are harmful globally. The change is rigorously governed, not just blindly generated. So, to summarize the whole shebang, algorithmic self-evolution is not about building a rogue autonomous agent. It is about continuous reorganization bounded by explicit goals, rigorous verification, and structural continuity. It represents a stable, harmonious transition toward highly adaptive systems, systems that continuously reorganize themselves while remaining deeply connected to the incredibly complex landscapes that we, the humans, design. Which leaves us with this final thought. We are entering an era where AI is graduating from just being a really fast executor of our procedures into a vast structural explorer of totally new possibilities. It's going to find pathways we never even imagined. So the big question is, as human landscape engineers, what new extraordinary landscapes will we ask it to navigate next? Thanks so much for joining me on this explainer, and I hope this helped you better understand the fascinating paradigm shift happening in intelligence today.